OK，right，我要重新讲一下，我一开始这个课的时候，不是我有说过，我的课我不要 spoon feed，说其实对于你们来说，我觉得啦，你们其实不知道 spoon feed 跟没有 spoon feed 的差别，其实，因为你们还没有真正去到一个没有 spoon feed 的环境里过，因为就算我在我的班上做一些不公平的事情，你们也不会注意到的，因为你们已经习惯了 spoon feed 的情况。spoon feed 什么意思呢？spoon feed 跟不 spoon feed，很大的区别在哪里呢？就是 spoon feed，你只要让你不会在思考的情况下，那个东西就是在 spoon feed 你了。当你没有在思考，在吸收的时候，那个就是在 spoon feed 了。其实。所以，比如说一个很简单的 example，就是以前我们上课的时候 tutorial，我老师跟你们讲，没有一次我们是讨论完过所有的题目。你会觉得哎不 efficient 啊，好像不什么这样啊。但是问题啊，它的重点啊不是在讨论完所有题目，那重点在哪里呢？这才是重点。它的重点是要你去 develop 这个 idea。当然你说会很慢，但是这个是起头，你要知道，这是起头。所以我们在那里读了差不多4年这样，所以我们是每一年是在慢慢的增长。所以我说你们在这里读书的时光是非常怎么说？非常嗯，非常怎么说非常怎么说？OK，第一很短，第二是你们在这里时间其实很少。OK，所以其实你们要每一年都在增长，其实 OK 了。你才会成长成一个比较成熟的思维啊。所以这个就会回答你说，数学系读来做什么了？如果你没有这个成熟的思维你说我会上 open，我会上 close 你就去做嘛，没有人叫你 open close，你明白吗？是你怎么去想这个 open，怎么去想这个 close，这个东西才会用在你的生活上，用在你的工作上。你明白吗？不是 close open 本身可以用在生活工作上，可能可以，但是不是最直接的。最直接的是你这个人的思维，你的想一个东西的思路，make sense？其实，在这个班有非常好的萌芽的那个种子，只是说你们没有很好的被 shape 所以你们还在起步。所以我不是会讲什么你们写的东西像第一年写的东西，有起步，但是没有很好被 shape 出来，懂什么意思吗？说你就要 catch up 现在就开始 catch up，at least 你现在还在这里，你还有可能半年，可能还有1年，这个就是你最珍贵的那种珍贵的东西你能够 get up from this degree，that's all。如果你不做 research 的话，哦，这个就是你要抓到的东西OK，还有一点是我知道你们很喜欢分数，我也喜欢分数。OK，so I mean，分数这个东西怎么拿嘞？这个分数我想跟你讲真的是你种多少因，你就会得多少果的东西。OK，因为我可以告诉你，我是很 fair 的一个人，我是很 fair 的一个人。OK，虽然可能你觉得我会欺负你这样，但是我是一个很 fair 的人。你该拿多少，我肯定会给你的。你有进步，我一定给你的。That's all，我只 look for improvement 罢了。OK，如果你给我很厉害的人，哇，比如说之前给我一个很厉害的人，他没有进步有什么用？我跟你讲这个最厉害的人到最后会到底的，他一定会到底线的。到了底线过后怎么办呢？如果他不进步，他就卡那边了咯，你明白吗？他一定会到某个底线的。可能他 calculus 很厉害， 可能他 abstract algebra 很厉害啊，到了后面呢 category theory 呢 category 之后呢啊怎么样呢？所以我们才要学习哦。OK，所以我们才一直要学习学新的东西。如果你觉得这个就是你的底线，good chance for you，你能不能进步？现在是这个进步才可以让你越爬越高，而不是你的起跑线还是什么之类的。很简单，我 proof 给你看。你如果可以看到报纸的话，天才以前不是很多天才吗？或者不时都会冒出一些天才。后来呢，天才在哪里？长大的天才呢？Some of them 委地种地。I mean，我们华人、中国人有一句话吗？小事了了，大未必佳吗？So the problem is 整个 progress 你有在进步吗？你有在追求更好吗？This is the main thing 啊。好，而我们数学可以做到这件事情，因为这就是数学的初衷嘛。我们想要 explain everything impossible，明白吗？好，可以吗？格局放大一点，你就整个人就会不一样了。哦，不要局限于那种小东西。你格局放大，OK，你 focus 放大，then 那些小东西会跟着来的，你不用怕，不要担心什么我出去有没有工作还是什么什么什么这样。你如果好的话，谁不要你？我问你，你明白吗？所以你要把 focus 放在自己，把自己做好，make sense？OK 了，合理吗？你觉得？你觉得合理吗？你要觉得合理哦，不然的话，我讲的也是没有用哦。呀，你可以追求啦，你可以追求各样的东西吧，啊，还是最终要回到自己，要吗？呀，好，So I mean 有什么问题？OK，你们尽量在我的班提出来，如果我能够做到的，我就 try 做。OK，因为我不是一个善于可以认识每个人的人。OK，我不是一个很会共情的人。OK，所以你要告知我，因为 for example，比如说一些 proof 可能很长啊，还是什么之类的可能在我眼里不长诶，你懂吗？所以我们有认知的偏差，所以你告诉我咯，KeySeng 这整个 proof 在做什么？OK，做什么呢？我就开始告诉你这个 proof 在做什么了，OK 吗？因为有时候我们会有认知偏差，因为你会有时候会看到一些老师会说，哎呀，this one obvious 啊，this one obvious 啊，this one obvious，为什么对你不 obvious？因为你跟他的高度不同啊，当你站到他的高度的时候，你也会觉得 obvious 了，你明白吗？说现在我我只能够依照我以前的高度来认知你们的高度，可能你跟我以前的高度不同呢，那你就要让我知道咯。OK，所以其中一个你让我知道的管道就是你的 assignment，其实啊，所以 that's why 我要 set 很多 assignment，为什么？因为我要 check 你，如果没有 assignment，我 check 不到你啊，我不知道你会还是不会啊，你懂吗？所以 that's why 我 set 这么多的 assignment 是每一个关卡我都要 check 你，然后你每一个都要进步。Of course 啦，我们 starting point 的时候没有来每一个 week 这样 feedback，因为某些原因，就其他学生的原因或者我的原因都有，所以就不是很好的一个 process 哦。所以我不是一个来 assignment 考一下就是分数，不是 assignment 对我来说不是分数，assignment 对我来说是看你的 progress，你明白吗？可以 get 到。所以我知道哦，原来你们写 proof 有问题，then 我会注意一下，可能有些比较重要的地方，我就跟你讲一下，哦，这边是这样的，那边是这样啊，不然的话我们就直接过了，我们讨论 concept 哦，这样哦，啊，明白吗？OK 吗？呀，说每一个考试啊，assignment 啊，我改啊，都是一个 feedback 的过程来的，你给我，我给你，你给我，我给你，哎，sorry，对，而不是一个只是给分数的罢了。呀，分数其实真的没有这么重要。OK，重要是你到底学了多少。你学的够多，分数肯定是你的，你不用怕。就是 if then OK，不排除啦，不排除啦，有一些社会不公的现状呢，这是有的啊。比如说我以前我 Matrix 啊拿4.0啊拿4.0，我申请医科医生啊 pharmacy 啊进入政府大学没有拿到，为什么？绝对不是你成绩不好，只是因为华大的 problem 种族的问题，没有办法咯。但是这个就是你生活的 land 上面，但是呢，你能确保什么？你能确保的是你自己是一个好料。如果你是一个好料，你走到哪里都是一个好料。make sense 吗？OK 了，OK，好，Yeah，好。所以在我课，你尽量 improve 就对了，你肯定会过得很好。因为我是很 fair，然后我不会欺压你，虽然可能题目很难一点啊，接受，就这样。好，哎，你学到的都是你自己的，不是我的。你学到了，你自己去开课了哦，是不是？对不对？呀，你别的老师学的东西，你开得了课吗？我跟你打赌看，所以你自己想一想啊。好，我一定会给你分的，你不要担心。如果你有进步，如果你真的会这个东西，你如果放心下去学，我保证你没有一个漏掉了。在我以前班没有一个漏掉了，只要你有放心去学啊，你不能讲哦，我有心，然后在家那边玩 game 啊，或者没有读书啊，这什么叫有心？这不是有心，有心要付出行动的，你明白吗？有心是要付出行动的，跟着行动的啊。OK 啊，Yeah，而且我 Office hour 啊什么啊，你都可以来找我啊，对不对？也可以 message 我啊，email 我。好，没有什么隔阂的啦，没有什么隔阂。好，你不要，你呀，没有什么隔阂的。好，也不用把我当神啊，我不是神。OK 吗？说最重要啊，是你要 feedback 给我，你一定要 feedback，一直 feedback，然后我再处理，看一下怎么处理。好，feedback。All right，where do we stop? Extreme theorem. Okay, wait. Okay, so last time we proved a result on from analysis of calculus, which is the extreme value theorem. So what does this extreme value theorem says? If you have a function, okay, continuous function from a closed interval a b to r, okay, then this f will achieve the maximum and minimum point. Okay, maximum minimum point. But in this proof, right, what did we use? We only use the compactness of this closed interval and also connectedness, okay, to prove it. Okay, so these are the property we use. In MA1, how do we prove it? I just proved it, but I forgot. How do we prove this MA1 in? How do we prove this statement in MA1? Extreme value theorem. If I remember, well, this is what we did. So we use what did we use here? We use Bolzano-Weierstrass theorem. Okay, every sequence has a subsequence that converges Bolzano-Weierstrass. So this is the compactness part. Okay, later we will introduce this kind of compactness. Okay. So compactness using sequence. Previously, our compactness are using open covering. Okay. Later, you will see how they relate. Okay. Yeah. So it's actually secretly a compactness proof. Okay. Right. So what do we do next? So from the statement above, right, there's one example we can look at. So you can see that actually the open ball and the closed ball, right, are not homeomorphic. Okay, why? Because a continuous image of a connected set is connected. A continuous image of a compact set is also compact. Okay, so if you can argue that hey, two of them, one of them compact, the other is not compact, then you cannot form a homeomorphism. Okay, so let's see which one is compact, which one is not compact. Have we proved that compactness is implied by closed and bounded? So before the string value theorems, right, what did we prove? We proved that a set is compact if and only if it is closed and bounded. Okay, closed and bounded. So in this case here, you can see that closed ball is closed and bounded. Why? Because closed ball is made up by what? Made up by the open ball and the boundary. So it contains all its limit points. Okay, so therefore it is compact. But how to see open ball is not compact? Right? If you want to show something is not compact, what do you need to do? And then of a infinite cover of B of open ball such that it doesn't have a finite cover. Okay, so I give this cover here, which is 1 minus 1 over n. What is 1 minus 1 over n here? What's this? What's the first term? Half. And then next term? 2/3. So it's increasing. Okay. So can you simply just take a few out of them and then still cover your space? You need to take, okay, there's infinitely many of them, right? You need to at least take infinitely many of them away. So you can show that there's no finite subcover of it. Okay. So if you don't know how to prove this, I suggest you do exercise. Okay, do exercise. Why it doesn't have a finite subcover? Okay, you have to do exercise. So when I say this, you have to do exercise. If you don't know, then you must do. Okay, I know you're thinking because I was like you before. The lecturer say there's no I actually don't understand one. I don't understand. I understand until if I write it down. Okay, but some of these arguments, right, I won't write it in class because it is a bit tedious sometimes. So you need to try out yourself. Okay, my algebraic topology teacher always says whenever he want to do proof, he will say, I don't want to do this proof in public. Then a lot of it he didn't prove. He just said, oh, if you want to know, you come to my office. Like that. So what does it mean? So meaning some of the proof is kind of tedious. You just need to write it out. Okay, in particular, this one is one of them. So how to show that there's no finite subcover? Suppose there is. And then do you reach contradiction? Okay, suppose there is. Does it make sense? I suggest you, when I say you do exercise, if you are a weak student, please do the exercise that I'm saying. Okay, please do. Okay, so if you can prove that this is an open cover that doesn't have a finite subcover, then this set is not compact. Okay, so one is compact, one is not compact. So you cannot have a homeomorphism between them. Okay, make sense? Yeah. All right, good. So this one is about compactness. Sure. I think we need to start new stuff today. Okay, we will start talking about uniform continuity. Let's see how uniform continuity pops in. Uniform continuity. Okay, so let's define. The distance from a point X to a subset A. Okay, this is what we have seen in our tutorial. Okay, so let's fix a metric space. And then A be a subset of X. Okay, say it is non-empty. Then for each X in X, okay, we define the distance from X to A. Okay, we define the distance from X to A. By what? So dxa should be what? Should be the increment good of dx of A for all A in capital A. Okay, so this is what you've seen in your assignment. And next, we will define a terminology called the diameter of a bounded set. Okay, what is a bounded set means? Anyone still remember? What does a bounded set mean? What's the definition of a bounded set? When is a set bounded? As a maximum and minimum, not quite right.
Center at some point in the that with the positive radius is.
So this positive radius have to work for all center, or every center has a positive radius? It's a bit different, no? It's a bit different. It's a bit different. Say again. Definition. Okay, a set of a bounded set. Okay, is what? There exists an M such that every distance is bounded by this M. Okay, so this is the definition we had last time. But the definition that Yihan said just now is a proposition from this definition. Of course, we can take this as a definition because it is a if and only if. Okay, so it's equivalent. So if I want to take this definition, actually, if you fix any ball with center at X, you just need to find that for that X, you have a N. Okay, so for all X, so this N might be depend on X. Okay, it's not one N that works for all ball. Okay, so bounded is what? Distance of every point is bounded by one number. Okay, if you can do this, then you can find a ball at any point to encapsulate all your set. Okay, this is what we have shown us. So in particular, we like to work with the point origin. Easier. Okay, it's easier because when you compute distance, you just compute distance with 0. Okay, so that's why we prefer sometimes the ball sit in the origin, but depends. Okay, depends. Right. Okay, so next, we want to describe this diameter then. So if you can imagine, I have a bounded set, then there should have a ball that cover everything. So what's this diameter then? Okay, is this diameter of some ball or not? Okay, so the diameter of a bounded subset A of a metric space is the number sup. Okay, supremum of what? Supremum of all the dA1, A2 or A1, A2 in A. Supremum of all the distance. Supremum of the distance. So can this supremum equals to the M we had just now or not? Is it necessary equal to the M we had just now? Not necessary, right? The M could be larger than the sup, right? Okay. What do you mean by close? No, I can if all the set is less than maybe 100, then I can put 1000 also still bound by 1000. You get what I mean? You get what I mean? So wait. So if DAB is less than M for all AB in X, then surely DAB will less than M plus 1 as well. Okay, for all AB and X. Okay, so this supremum here might not be the number that bound your set. Okay. But is it reasonable to call it diameter or not? The supremum. Is it reasonable? Okay. I think it's quite reasonable. What is diameter? You can think of it diameter of a circle, right? For every point inside the circle should be within the diameter. Yeah. Okay. All right. So we'll prove a lemma here. So let's put this lemma. So this is called the Lebesgue number lemma. Let A be an open covering of the metric space X. If X is compact, then there exists a delta greater than 0 such that for all subset of X having a diameter less than delta, there exists an element in your open cover such that this element contains your B. For all B, for all B that having diameter less than delta. If this exists, right, okay, the number delta is called a Lebesgue number for the covering. Okay. So it depends on the covering of a metric space. So try and think about this again. So if you have an open cover of a metric space and it is compact, right? So meaning this open cover has a finite subcover. Okay. So you can imagine that, or you can have finite subcover cover your space. And it says that if your space is small enough, how small is it? Okay, the diameter have to be less than delta. Then this subset will live completely in one of the open set that cover the whole space. Does it make sense? Can you imagine the picture? So set X, right? And then maybe you have open covered it. Okay, maybe I draw a bit exaggerating. is not outside the set. Okay, then if your subset is like diameter less than delta, then you will live in one of the covering. But you see, if my ball look like this, if like this, also delta. But this theorem tells you what? There's another A that contains this. Okay, can see? Can see? Okay. So even if you, as long as you make sure your set have diameter less than delta, then you will have one A that cover you. Like that. Okay. 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 So how should we prove this? Okay, let's see how should we prove this. So of course we will start with any covering of X. That's what given in the question. Okay. What happened? What happened if X is one of the element? What happened? What happened if X itself is one of the element of A? Huh? What happened if X is one of the open set inside the open cover? You want to find what? You want to find a delta such that every open set has diameter less than delta. Your subset is in A. Sorry? Already done, right? No matter what delta you pick, every subset of X should be in X. Oh, so this is a trivial case. So if X is already in one of the open set in your open covering, then what? Then any positive number is a Lebesgue number. Because every subset of X surely is in X, no matter how big you are, how small you are. Okay. In particular, no matter how big you are. Lebesgue. Lebesgue. It's a Lebesgue number for A. Okay. Everyone follow? Okay. So we will assume that X is not an element of A. Otherwise, trivial. No matter how big, your subset is already inside X already. And X is one of the element in A. Okay, you already found an element that contains every subset. So if this is not the case, then what happened? Then by compactness of X, what we can do? We can actually choose a finite sub collection of A. Okay, let's pick a finite sub collection of them. Okay, that covers A. Okay, and we're gonna play a trick here. Okay, so what trick is this? So for each I, we will look at the complement of AI. Okay, for each I, we look at the complement of AI. And then we will compute the distance, okay, from every point in X to the complement. Okay, later you will see why does this work. So we'll define fx to be 1 over n of sum of I minus 1 to the n of the x ci. Okay, does everyone see what this is trying to do? For every x, I compute how far this x is to the complement of AI. And then I sum them up. and then I take the average divided by 1 over n. Then later you'll see how useful is this. Okay. Can everyone follow the construction here? Yeah. Okay. So what we will show is this function is always strictly greater than 0 for all x. Okay, this function should be always greater than 0. Okay, so how do we show this? So this is the first thing we will show. We will show that this function is always greater than 0. So let's show this. So let's take 1x in x. Okay. Then since AI cover x, right? That means this x should be living in one of the AI. Okay, so we pick I so that x is in AI. But AI is open, right? Okay, meaning what? Then we can found an open ball, say, with radius epsilon, such that b epsilon x is in AI. Okay, but what does this mean? What does this mean? So let's draw it out. So let's say you got an AI here. Okay, and then you have a ball with radius epsilon inside here. So this means what? How can you compare this point with the complement of AI? How far is it from the complement? How far is it from the complement? Where is the complement of AI? It's outside here. So how far is it from the complement? Yes, so the complement distance of x with Ci should be greater or equal to epsilon. Correct or not? 如果你站在这个门前面呢，你距离这个门有2米，连外面的人跟你距离多远？最少2米哦。This is the part you can use in real life or maybe ball no use. Correct or not? Yeah, okay. So 这种简单逻辑，我可以跟老师跟你讲啊。进去了，这里的 AA 可能连这种基本的逻辑都不知道。OK， 不要 AA 啦 ，admin。OK， so that's why 搞出很多笑话，你们去跟这些 admin 人 deal 的时候，因为他们有时候他们 simple logic 没有。Exactly 那天我跟我一个 AA 拿一个名单，他讲他没有，他叫我去跟另外一个秘书拿名单。对，就是推。OK， 不要，他推到一个境界是来，我去另外一个秘书，我问他，我要跟你拿这个名单，他讲没有，你要回去第一个那边的，我变成一个 loop 了这样子的话，我讲没有，是第一个叫我来跟你拿的。OK， 他讲 OK， 我去问一下第一个人。后来谁给我的？你们猜？没有，第二个给我的。对，所以是停在第二个。对啊，是咯，所以说，因为他们基本的那种讲SOP 他们没有，基本的 SOP。呀，最 basic 咯，有了逻辑过后要有 SOP 嘛，大概大家知道要做什么嘛。现在是自己不知道自己做什么，问题是说就会很乱哦。OK， 呀，说学一下数学去救一救马来西亚好不好？OK。Yeah， 这个更重要 ，Pure Max 还没有这样重要，救一下我们国家。OK， so consequently dx and c1 is greater or equal to epsilon. So that what? So that fx is greater or equal to epsilon over n. Okay, one of them is already epsilon. Yeah, and then divide by n, that term is epsilon over n. The other term, matrix is what? Matrix is always greater or equal to 0. Okay, you have at least epsilon over n. All right, so good. We have shown that fx greater than 0 for all I. And what? So second part, since f is continuous, okay, it means what? We put this after extreme value theorem, right? Since f is continuous and x is compact, it has a maximum and minimum value. So in particular, we are interested in the minimum value. Okay, let's call it delta. Why do I call this delta? Why? Why? Why you sell? Why? Why do I call this delta? This is, I want to claim actually this delta is the thing I want already. Okay, so we want to claim actually, we want to claim, want to show that delta is the Lebesgue number we want. So that's the reason why we put them the same name, not by chance. I want to show that this Lebesgue number. Okay, you see, minimum. I'm taking infimum of a number that's greater than 0. What could that infimum be? I made one question. So if you have a set of number that's positive, what could the infimum be? Bigger or greater to 0. But what I want to claim here is not that it cannot be equal to 0. Okay, what I want to claim that this has to be greater than 0. Why? Why? Logic. If you want to show that it is not equal to 0, then you can do direct proof or contradiction. What happened? Or otherwise, what happened if delta equals 0? What happened if delta equals 0? Hey, say again. Sure, there exists. Wait, there exists. Is it true? Let me write down first. There exists x in x such that fx equals 0. Correct? Why? Because we achieve it. We achieve it. It has a minimum. So this guy is achieved by some value. Okay, some point in x. Which means what? Which means by definition of fx is what? There's this x such that for OI, dxci is actually 0. Because we are summing positive thing. To get 0, then everything have to be 0. Not negative, not positive. Not negative. And then what? By definition again, there's this x in x such that for every I, infimum of dxa of a in ci is 0. By definition again. And what does this infimum means? For this particular x, and for every I, and for every epsilon greater than 0, there exists ai in ci such that the distance of x with ai is less than epsilon. Fair enough. Infimum definition. Is it true? Infimum definition. Okay. So where's the contradiction? Says what? What this says? What does this say? It is arbitrarily close to every complement. Arbitrarily close to every complement. A complement of what? A. There's a lot of A here. Like there's a lot of why is my CJ? What's my CJ doing? C is defined as a complement of A. Right. Correct. Good. Yeah. Oh, you mean the big A? Right. Okay, good. Yeah, right. Okay, so I mean, what am I thinking about? Okay, what I want to say is that this X is arbitrarily close to any complement. Okay. But could it happen like that or not? Okay. But what do we know? We know that AJ should cover our set, right? So meaning this X, right, should be living in some AJ. Okay. And like what we did just now, AJ is open. So we can find a ball around X such that this ball is living inside AJ. Same argument like just now. So what? Then it is impossible to find something in the complement of AJ such that D of XAJ is less than R. Okay, no? Does it make sense? Okay. Yeah, you say you can arbitrarily close to A complement AJ, right? Actually, you cannot because there's some ball that contain U already. And then that ball has some radius R. Okay. Yeah. So the person outside AJ should be at least R away to you. You cannot arbitrarily close to something outside. Okay. So yeah. So there are two things to bridge for you in pure maths. Okay. One is the language. Second is the concept. For 8 years, I study pure maths. I'm trying to sync these two skills. Okay. Trying to sync these two skills is 就是很简单的白话文，就是说怎样把你所想的东西清楚的表达出来，这就是 pure maths 要做的事情。所以这是你要学到的一个 skill。如果你要读 pure maths 的话，怎样把你想到的东西清楚的表达出来。OK， 所以意思说人家是透过文字知道你在想什么。OK， 不是靠你去比手画脚用各种各样的辅助工具。OK，so that's why this is the birth of language actually. So language is very logical one. Okay, what's the logic behind every language? Is the logic behind the races. Okay, how they think about, how they perceive this world. Right. I think I gave you an example last time, right? About pisang goreng and goreng pisang. I mean, pisang goreng and fried banana. Okay, why one races put fried first? Why one races put banana first? Okay, yeah. And actually, there are different races that adopt to these two ideas, right? For example, in Japan, they also use pisang goreng. Okay, like fried banana, who use it? For example, English, no? Chinese, no? Also fried banana, 炸香蕉，没有香蕉炸，对不对？炸香蕉。Okay. So yeah, these are the logic that different people adopt, and yeah, so they take out all the combination between these two words, right? There's only two combinations, right? Only either fried banana or banana fried, right? So all combination got people takes it. So this means what? Actually, our society is very vibrant. Yeah, it's very vibrant. Everyone will take different convention. Okay, yeah, but by studying maths, I don't force you to accept this convention. It's just that if you want to talk to me, maybe you need to use this convention. Okay, so as a pure maths, you learn different branches, you learn different convention to talk with different branches of people. Okay, now. And there's a very grain unification project in mathematics, which is called the Lang programs. So Lang programs is trying to bridge different branch of mathematics, for example, analysis, for example, algebra, for example, geometry. So they have different conventions, but we want to bridge them together, hold them together. So what's the tool to hold them together? Actually is representation theory. Okay, so representation theory will connect all branches. Okay, good. Let's finish up this proof and then we will take a break. So we show that delta have to be greater than 0, and then we want to show that this delta is the one we want. So what do we need to show? We need to show that for every one set that has diameter less than delta, there exists some A in A such that this A contains all such B. Okay, this is the last thing we need to do. So if you want to show for all B that has diameter less than delta, right? So what do you need to do? Fix one first. Okay, fix any one. So now let B be a subset of X of diameter less than delta. Okay, I want to show that it contains in one of the A. So to show that it is contained in one of the A, what method you can use? So let's draw it up. So let's say this is A. Let's say one of the AI, and then you have a B inside here. Okay, with diameter less than delta, diameter like this. Okay, it's B. So how to show it? How to show this? Can you relate to the complement or not? Since we define a function on complement. So let's say there's a point here. Is there any way to relate this B to the complement or not? Is there a way? Relate to the complement. Let's say this part is the CI. But we never like develop any property using diameter. Only thing we know is the diameter is sum of all the distance between any 2 points. Okay, if not, let's continue first, see does this proof make sense or not. So let's say we have this set already. So what can we do? Because this is non-empty, right? We simply pick a point x0 of B. Okay. So instead of looking this B, we form a ball of B delta x0. So does this make sense or not? Is it true that for every point of x, it is delta away from x0? Is it true? Why? Why? So x0 is a point in B, right? Okay. Why other point is only delta away from x0? No. Sorry? What's diameter? What's the diameter? Diameter is the sum of all the distance, right? So in particular, every point, the distance between every y with x0 is lying inside the set of the sum. And the sum of all this distance is d. So all the distance between y and x0 should be less than or equal to delta. Does it make sense? Yeah. Can follow? If cannot, you just say cannot. So that is for every y and b, dx, dy x naught is less than or equals to the sup of d of x. Maybe use a1, a2, or a1, a2 in b, right, which is equals to d. Yeah, it's very simple concept. Okay. Okay, good. So what can we do next? Now, what can we do? So we use a similar trick just now. So we can see that delta should be less than or equals to fx naught. Delta is less than or equal to fs naught. Is it true? True or not? Delta should be less than fs naught. What do you mean by fs naught outside? Fs naught is a distance or sum of distance, right? So yes, sum of a distance from n to n such that this is 1 over n times d of s naught with x i. Hey, sorry. 1 over n squared. Okay. Okay, so why is it true? Everything is at least the Yes, just now what did we say? Delta is the minimum value. So there's nothing to do with this definition actually. It is just by the assumption on delta. Delta is the minimum of this function. Otherwise, if you use this, then still got something might happen here. But we assure this is the minimum because this is from the how we pick this delta here by the S-string value here. Okay or not? Okay. But how nice is this? How nice is this? Then this function value here is actually less than sum dx naught cm. Okay, where dx cx naught cm is the largest out of all ds naught ci. Okay, correct or not? Because you are taking the average, right? So your average should be less than or equals to the largest number you take. Make sense? Make sense or not? Your average should be less than or equals to the largest number you take. Okay, then we are almost done already. Can everyone see what is happening, what's coming? Then what? What's coming up? What's coming? You are delta. You are delta away from the outside. But all your things is less than delta. Huh? Triangle? No. Do you need to use that to show it? So my claim is this delta ball should be living in AM. Okay, which is equals to x minus xm. Okay, does that make sense? So let's draw it. Let's draw it. So let's draw our ball. How about we just use this guy here? Okay, so previously what we know is the diameter, but now we know better. So if I fix a x naught, I can really find a open bore. Okay, that have radius delta from the x naught. Okay, seems like this radius is easier to use than the diameter. Okay, and then what have we shown? We show that what? This S naught, right? How far is this S naught from the SM? It is greater or equal to the delta. Okay, it's greater or equal to the delta. So your C1 may be as much as here. But everyone follow or not? Follow or not? Okay. So your CI, your CM, okay, in this case CM, your CM is everything outside the open bore. Meaning what? Think. Can I deduce that this ball is in AM or not? At least delta away from the outside. Okay, so if your distance is 2 meter, okay, 2 meter. So your ball is 2 meter from you. But you know your outside is at least 2 meter. So your open ball should be living inside AM. Make sense or not? Got question? Question? Yes. Okay, repeat again. So let's say you have a 2 meter ball from you. This is open. So the boundary is not included. Okay. But you know that you and outside is at least 2 meter. At least. So is it true that the open ball of radius delta is living inside in this case? Think. This is a thinking process. You must think. Okay. Is it true? The claim is true. So you need to think, why is it true? At what distance? Okay, how to understand this this statement here? How to understand this statement? Distance of S naught with CM is greater or equal to 0, equal to delta. This means if you walk maybe delta away, you're outside, maybe. Okay. But it's not exactly outside sometimes, because we are looking at infimum. Okay, maybe you are arbitrarily, if you are at delta, you are already arbitrarily close to complement to complement this. Okay, yeah, not exactly achievable sometimes, but you are already arbitrarily close to the complement. But if you don't work delta, surely you are some distance away from your complement. So you are in a complement. Question. Ask. You just ask. That's fine. Because different people have different way of thinking. Question. Yes. Where? This M, yeah, where this M is from, This M is coming from this inequality here. So we have shown that Fx naught is greater or equal to delta. But what is this Fs naught? How do we define it? We define it as an average of ds naught di. sum of distance with the complement. And then you take average. Okay, you take average. But this average surely less than one of the largest term. This is how we determine the CM. Okay, and then we claim that the ball of radius delta is inside AM actually. So in the complement of complement. Okay, complement of CM. Okay, because how do we define CI? Oh yeah, complement of what? Okay, you should ask actually. So what I'm saying is it is living in the complement of AM. So which is AM? Yes. Yes. That's right. That's right. Yes. I mean, if you want to show this, yes, okay. I think if you want to show this, you can only use contradiction, but I think contradict the delta thingy, the delta. You will contradict the delta. If there's some point inside here which is not in here, it will contradict the delta, the choice of delta. Okay. Any question? Other question? Any question? Yeah, if you don't convince, right, I suggest you to write down this argument here. I think you can only use contradiction, I guess. Because if you try to take one point here, okay, just now you say, who say want to use triangle inequality? Oh, you say you want to use triangle inequality, is it? But I mean, how to show something is in here? You want to show something is here, then you have to be in here. To show something is in here, then how to show something is in here? How do we learn about this guy? So I think you need to use contradiction to contradict the choice of delta, I think. Contradict this line, I think. This is what my first thought. Yeah, this is my first thought. If there's something in here that's not in here, then I think you will contradict this step. If you still don't convince, try write down why this part is true. Okay, this is the spirit of mathematics. Yeah, try write down this part. Why is it true? Yeah. Okay, but I think, yeah, okay. I have to stop it like this here. Yeah. There's always some point we don't feel satisfied one. This is the, how to say, maybe people who learn mathematics, the similarity, the topic. But this is good because you need to dig it out. Why is it true? This is how we advance our max knowledge. So for example, the set theory, not good enough. Hubert said not good. Okay, we want to go to foundation of max. And then it turns out that Golder say, oh, cannot. No matter how you push the foundation further, you still have something that you cannot be proven by that system. Then you need to create more, but Golder say, still got some statement that you can create that you cannot prove using that system. So this is called the Golder incompleteness theorem. Yeah, Golder was trying to answer Hubert's question. Can we build a ultimate foundation for max or not? Turns out cannot. For any system you build, there's some statement that you cannot prove within itself. Okay. Yeah, let's take a break until 1:32.
Right, this is enough.
See?
And
this is true, and this is correct. And then this definition only, right?
then you have this. So
anything
and this is inside. Well, anything.
think. Right. So what?
So we want to show this one.
Mm-hmm.
And S minus CM, let me think. Strong.
S minus CM. Unless you can put here DS AM. AM can or not? Because I need to be careful, because this is a real distance, but this is an infimum measuring. So infimum sometimes infimum, how to say infimum? Infimum is arbitrarily close.
Yeah. Some problem, I think also. Let me think also.
Yeah, you see, if there's this point in B delta X naught, such that Y is not in AM, what will happen? Meaning that this point need to be not in the complement of CM, which means what? This point is in CM. But if this point is in CM, wait. If this point is in CM, this implies what? dy with CM is what? 0? Contradict what? In this line. Okay, yeah. Yeah, so this is what I want to say. Hello. If it's in that ball, not in that, then you have contradiction. Okay, yeah. So, Which way? Which way?
You show the distance between A and B, but the subset.
Oh, you mean directly, yeah? I think directly.
Distance problem, so maybe there's.
Because directly, the problem of directly is you need to show that every point in B is in this AM. So how do you decide it is in AM? This is the problem. I know how to describe point in the ball, but how do I describe the point in AI? Because this AI also depend on X and depend on your metric space.
At first we define this B delta because
no, B delta definition is very easy. It's just all the point is delta distance from S naught. So this delta distance, this S naught is fixed in every.
I remember we start with B is a subset of A, and then you pick some point inside, such that this B is bounded by this B delta, right? Then you don't have to.
No, I mean my problem is I don't know how A looks like, so I cannot show something is in A. What I know is like they are relative distance, so I can only play things with distance. I cannot say exactly. Which supplement influence?
The distance
I mean, we just
due to this.
maybe not quite, and not quite. Just that that too maybe helps. The supplement infinite thing, I think, is because maybe we want to deal with infinitely many points. So you need to consider all possible. Yeah. 什么？Sam 就是
你们
就是这个 argue 为什么那个 ball 是活在 AM 里？对，所以用 contradiction。Suppose 里面有东西是不在 AM 里面的。direct proof 是可以，但是我们不能够来讲啊。讲啊，就是 direct proof 可以。怎样呢？你说说看。Yep.
这样子呢，交大会你这个包会完全在洗完的时候，它就整个包都会在。
喂，再来一次，我有这个 delta， 然后 delta 跟水的 CI 什么关系？我只知道它和 CM 距离是
Y 和 X 的距离小过所缺的 C。
Okay, how about let me draw it up. So let's see let's say 这个是 CM. Okay, CM 和 delta 的距离是大于等于 delta， 对不对？ Then 对不对？ Then 你是说我就直接做一个 open ball 在这边，这个意思？是这个意思？哦。对啊。So I mean 这个 ball 其实是 open 啦 ，open like this。Yeah. So everything less than delta should be outside the complement.
所以说它的 converse 就是如果小于对，那就不在CM。
哪个 converse？
counter positive。
对，
如果在 CM 的大于等于那个delta，然后反过来就是如果小于 delta，就在 X 减 CM。
如果大于 delta， 它就在 CM 里面。
如果大于等于 delta 就在 CM 里，然后就反过来的话，如果在，
所以这个有一个危险的地方，其实它不一定要在 CM 里，它不一定要在 CM 里，只是那一个点会无限的接近 CM， 对吗？因为 dx not CM 这个东西不是，它是 infimum 它不一定要 realize 把一个里面的点是 infimum
如果在 CM 大于等于，然后如果小于的话就不在 CM， 还是 counter positive。
但是我想 argue 的是说，如果它是大于等于CM 的话，那个点不一定要活在 CM 里，只是那一个点是无限接近于 CM 嘛。所以其实还可以再大一点，其实这一圈还可以再大一点。 外面这一圈还可以再大一点。Okay, is it okay? Everyone okay or not? Okay, right. So just now in the break, I hook up this contradiction proof. Maybe you can try and look at it. Suppose there's point in B delta such that it's not in A, M, and then it doesn't work. Okay. If you still want to think about this direct proof, I suggest you to think about it. Yeah, try and think about it. Okay. Yeah, try and think about it. Okay, definition. So we're going to deal with this uniform continuity. So let f be a function from metric space x dx to y dy. Okay, is uniformly continuous. Okay, if I think this is the same as what you have known. For every epsilon, there is a delta such that for every point x0, x1 in x, if the distance between x0 and x1 is less than delta, then the distance between fx0 and fx1 is less than epsilon. Okay, so the difference, what's the difference of d here? So if you look at the d in x, you should use x matrix. If you use y, distance is y space, you need to use y matrix. So the theorem here is the uniform continuity theorem. So what does the uniform continuity theorem says? When is a function uniformly continuous? So let f be a continuous map from x to y, okay, such that x is compact. Then f is uniformly continuous. Okay, then f is uniformly continuous. Any idea how to prove this? Okay, maybe ask you to discuss. Try and discuss and think about how to prove this using the Lebesgue lemma. If you 3 minutes, think about how to get this delta. It's not a coincidence why we call this delta. I think about this. How to get a delta that works for all epsilon. Using the Lebesgue lemma. And talk with your friend. Use Lebesgue lemma. Oh, okay. Go back to Lebesgue lemma. Okay, how about I copy it down so that you can look at them at once. So, okay, let me copy this. Together. Okay. Okay. Yeah, you can compare the property and then see how you're going to use it. Okay. Any idea? Any idea? Okay, if you don't have idea, you must know how to start first, right? How to start? Correct. I mean, how to start your proof? You want to show something is uniformly continuous. So, I mean, what's the tool you need to start with? Epsilon, right? You start with epsilon first. You start with epsilon. Fix an epsilon. Okay. You want to show distance of 2 points less than epsilon in the image. Okay, of H. Okay, so what do we do here? So really, we consider an open covering of Y by B epsilon over 2, 1. Over. Okay. So if you see this epsilon over 2, what should you think? In the epsilon delta proof, when you see epsilon over 2, epsilon over 3, what do you think? What am I trying to do? Yeah, maybe some unique 2 part of epsilon. Okay, so how this 2 parts comes in? Yeah, let's see. So let A be the open covering of X. Okay, so how to get this open covering of X? Simply take the inverse image of this ball. Make sense or not? Okay, I take the inverse image of this ball. Correct? Okay, I look at the image set and then I look at the inverse image. And then they form a covering. Why? Because the inverse image of a continuous image is, or of a continuous, the inverse continuous image of an open set is open. Right? Because this is the continuity definition. So what can we do here? By Lebesgue lemma, okay, we have a delta. And then I want to claim that this is the delta that we want. Okay. So we have a Lebesgue number for this open covering. Okay. And I want to claim that this is my delta. So if to claim this is my delta, right, what do you do? Then you simply consider x1, x2 such that dx of x1, x2 is less than delta. Okay. Then what? Then what can we do? What happened to this 2 point? What does this lemma tells you? What happened to this particular set of x1, x2? That has diameter less than delta. So by Lebesgue, by the Lebesgue what? Lebesgue Lebesgue lemma here, what do we know? So let's write down what you need, what you have. So that there's this and inverse image, right? Inverse image of bow of radius epsilon over 2 y. Should we give it a name or not? It's better we give it a name. Let's say A, use A again, such that F1 S2 is inside A. Correct or not? Go back to this statement here. So you have a covering, okay? What does this Lebesgue number do? If the subset in your X has diameter less than delta, then your subset is living in one of the element of your open cover. But what's your open cover here? These are the inverse image of ball of radius epsilon over 2. So you are leaving one of the inverse image of ball of radius epsilon over 2. So what does this mean? This last part. This means that the image of x1 and x2 actually what? Actually is living in some of the ball of epsilon 2. Make sense? You apply F to both sides. I don't know. This is some ball. The inverse image of some ball looks like this. So you apply F, it becomes this ball. You apply F, it becomes image. Okay. Right. Then what is the distance of fx1 and fx2 in this case? Less than or equals to dx1 with the center y plus d with y and fs2. So you have epsilon over 2 plus epsilon over 2, which is epsilon. Okay, so done. So you see, in this, general proof of uniformly continuity, actually we invent a new notion, which is this Lebesgue number. But in maybe MA1, okay, we only see maybe compactness, okay. But in the general compactness, we actually found this Lebesgue number here. Okay, yeah. So when we sometimes when we prove general statement, new notion might be introduced. Okay, new notion might be introduced. So that's why we go for more abstract, more pure, more abstract, more pure. Because when you go more abstract and more pure, maybe you will see even more detailed stuff happening. Okay, does it make sense? Okay, no. Does it make sense? Yeah, more detailed stuff. You don't just see the compactness property. Actually, from this compactness, you extract out a special number, which is delta. And what do you mean by generalization here? Yeah, we are generalizing compactness. From this generalization, we pick out a special number, which is the Lebesgue number. Yeah. Okay, no? Yes, question.
2 points that has distance, has diameter less. Why is it less than?
Yeah, why is it less than delta? Because their distance is less than delta. So suprema or the yes. There is a possibility, but in this case, it is not right. Because the suprema is achievable by this number, less than delta. There is a possibility, but I mean possibility from the definition, but in this case, it is not right because what is a sup of D of this set here? There's only 2 things you need to consider. Or I mean 3 things maybe, because you can consider S1, 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 S2, S2, S2. So out of these three numbers, which one is the largest one? Must be the D of X1, S2. And D of S1, S2 is S1. Because this is 2-point set, so you don't need to have an infinite consideration. Okay. Okay, what time is it? Not enough time. Okay. So maybe let's quickly go through this part here. Maybe I don't want to prove the subsequent statement given by Moncrief, but I thought it is pretty to include in the lectures, not? So next, actually, we didn't define isolated point in topological space. Okay, we didn't really define this in topological space, but in metric space did we define? Yeah, in metric space we defined it, but in topological space we haven't really defined it. So how to define isolated point in a topological space? We say that a point is an isolated point if the one-point set is open. Okay, I think quite intuitive. It is isolated if that point is already open. Okay, it's open neighborhood. Okay? One of the open neighborhood is itself. And surprisingly, from what we did, we can show that R is uncountable. How do we show R is uncountable last time? We used the Cantor diagonalization theorem. Okay, so that is algebraic. But actually, we can show it topologically. Okay, using compactness. Okay, using compactness to show that. So first thing we show is if your space is non-empty compact Hausdorff space. So this you can think of it like the closed interval in R. It is compact, first of all, closed and bounded. Hausdorff, okay, in R is quite easy to see, right? It's Hausdorff. You can find an epsilon to avoid. But the thing that says here is if this kind of space has no isolated points, then what? Then this space is necessarily uncountable. Okay. For this space is necessarily uncountable. And this proof uses topology, the compactness in particular. Okay. And the corollary of this proof is every closed interval in R is uncountable because closed interval satisfy the property just now. No isolated point. Okay. Should we go discuss this proof next time or not? Or you can read it yourself? Go through together. Sorry, now not enough time, but next lecture. Do you want to go it together or? Oh, our schedule is not enough time or not, huh? Okay, my plan is like this. So even if you we want to discuss it, I think we will just run through. We won't go into detail because this proof is not very important for us. Okay. Not very important. Okay, sure. Yeah, you can read it. So if you don't understand, surely we can discuss together. That's one for sure. Okay. So next time you come to class, after you read, you don't understand certain part, and then we can discuss it in class. Just that maybe we don't discuss it together. Okay. But the main point of this proof is using compactness. Okay, compactness, not the Cantor diagonalization theorem. Okay, compactness. All right. So I'll see you tomorrow.